So for these notes, we are looking at the quadratic parent function. And remember that the parent function is always the function in its most simplistic form. H and K are 0, A and B are 1. Okay, so there aren't any transformations that we're going to see. For every parent function that we see from here on out, we're going to have a set of parent function points that we use to transform the function. And the reason these are so important is because every function has a specific shape. As we start to stretch, compress, and shift, and reflect, that shape could get distorted. And so that's what these points help us to maintain. All right, for a quadratic, the x values go from -2 to 2. And if you're not good at memorizing points, just know that x goes from -2 to 2. All right, well, plug it into the function. What is -2 squared? 4. -1 squared is 1, 0, 0, and so forth. So those are the points for our quadratic parent function. As you graph them, we'll notice that yes, just like the absolute value function, it's a symmetrical graph, but it is not straight on both sides, okay? This is curved, and there are arrows on either side. The vertex, our HK, is 0, 0, because we don't have any transformations. So it follows suit that the x-intercept is 0, 0, as is the y-intercept. The domain for our quadratic parent function is all real numbers because there aren't any values for x that when substituted into the function will not produce a corresponding y value. Okay, there's no restrictions. So we could say all real numbers or -infinity to positive. The range, listing from smallest to largest starts at the vertex. So we say that y is greater than or equal to 0 or 0 inclusive to infinity. For the increasing and decreasing intervals, these are always discussed with the domain. In other words, we always say, oh, from this x value to that x value. What does it mean? Well, if we read the graph from left to right, as x goes from -infinity to 0, the y values are decreasing. So our decreasing interval goes from -infinity to 0. And as x goes from 0 to infinity, our y values increase. So our increasing interval is from 0 to infinity. It is not 1-to-1 because it does not pass the horizontal line test, which means that there are 2 x's corresponding to 1 y. Our rate of change varies because it is not a constant, there is not a constant rate of change from one point to the next consistently. Our axis of symmetry is always x equals h, so for us it's x equals 0. The parabola opens up, so there is a minimum value. Reminder, minimum and maximum values are always discussed with the range. It is always the k value. So our minimum value is 0. There is not a maximum, and our horizontal asymptotes, our vertical asymptotes do not apply to this function. So there's the quadratic parent function. Now, we are going to look at the variations. It's important to note that there is a b value. So let's rewrite this as a parentheses b inside of this quantity that's being squared so that we can see, oh, right, gotta factor out the b value. For this example, let's go ahead and identify what a, b, h, and k are and write what transformational effect they have. So our a value is 2. A is always in front of the function. And since 2 is greater than 1, that means we're going to have a vertical stretch. Our b value is 1, so that means we do not have a horizontal stretch or compression, nor is there a reflection. Okay, so let's keep going. H is 5. Opposite sign always, so that means we go 5 units to the right. Our k is the same sign, so that's -4, which means we go 4 units down. Vertical translation. Now, I've said numerous times that the transformations have the same effect regardless of what the function is, as does the transformation chart. So here's what it looks like. It is 1 over b times x plus or minus h. Because both b and h affect the x values, h plus or minus is because whatever sign we take with it. And then a times y plus or minus k. Again, whatever k is. And that chart doesn't change. So if we can get comfortable with that, we are rocking and rolling. Let's use that as a guide, all right? Our b value is 1, so it's just x plus 5. And then a is 2, so 2y minus 4. Now on my screen, you can't see the parent function points, and I always like to have them just written down so that it's easier for me to substitute them into the chart. So I will always write the parent function points next to the transformation chart. This is a personal preference, absolutely. You do not have to do this. So let's take our x values and substitute them in. The first one is -2, so -2 plus 5 gives us 3. And then we have -1 plus 5 gives us 4. If we take 0 and substitute it in for x, we get 5, and then 6 and 7. We're going to do the same thing with the y value. So if I take 4 and substitute it in for y, 4 times 2 is 8, minus 4 gives us 4. 1 times 2 is 2, minus 4 is -2. 0 gives us -4. And the nice thing is that this graph is symmetrical, so the y values will repeat. Now when graphing, we know that 0, 0 is normally the vertex, so this is our vertex, but we also knew that from pulling hk out of the equation. So -5, -4. 6, -2, I can reflect it, and then 7, 1, 2, 3, 4. Now please, do your best to make your function look curved and put arrows at the end. Sweet. All right, characteristics. We just talked about the vertex. It is our hk, so that would be 5, -4. The x and y intercepts. Now I can see that x intercepts exist, but I don't know what they are. I know I'm going to have to find them algebraically, so I'm going to wait. Same with the y-intercept. I know that it's going to exist, but I don't know what it is yet, so let's wait. The domain is all real numbers because, again, there aren't any restrictions on what I can plug into the function, so I could also put -infinity to positive. This parabola also opens up like the parent function, so I'm going to say that the range starts at the k value, so y is greater than or equal to -4, or we can say -4 inclusive to infinity. The graph decreases at first from left to right. So as x goes from -infinity to 5, our y values are decreasing. And then as x goes from 5 to infinity, the y values increase. It is not 1-to-1 because, again, it doesn't pass that horizontal line test, and the rate of change varies. Now, axis of symmetry, that's always x equals h, so we have x equals 5. Again, this opens up, so we have a minimum value. It's always the k, so this is -4. Therefore, we do not have a maximum, nor do we have our asymptotes. All right, haha, the x and y intercepts. Algebraically. In order for us to solve, remember, if I'm an x-intercept, I lie on the x-axis. So I'm going to substitute 0 in for y, and I'm going to solve for my x. So 0 is equal to 2 times the quantity x minus 5 squared minus 4. And just like we would with an absolute value function, we'd have to isolate the absolute value bars. We need to isolate the grouping symbol from which x is inside. So I'm going to add 4 to both sides. So 4 is equal to 2 times the quantity x minus 5 squared. Divide by 2. So 2 is equal to the quantity of x minus 5 squared. Now, in order to get rid of the square, in order to get the x out of that squared quantity, we have to apply the inverse, which is the square root. But be careful, because if you remember, if I square 2, 4, right? But what if I square negative 2? Oh man, I get the same answer. So when you're working backwards, when you're taking the square root of a number, you have to account for the fact that you could have two different answers. So we're going to say that x minus 5 is equal to plus and minus the square root of 2. Add 5 to both sides. The radical should always go at the back, so we have x is equal to 5 plus or minus rad 2. And I'm not asking you to graph it. I'm not asking you to tell me what it is in an approximation. I just want to know that you can find it. So our last step is to write it as a coordinate. You're more than welcome to write it as two separate coordinates, but one will do. All right, last but certainly not least, we have our y-intercept. So substitute 0 in for x. We get 2 times the quantity, 0 minus 5 squared minus 4. So 2 times the quantity of negative 5 squared minus 4. Negative 5 squared is 25. If I double that, I get 50. And then if we take 4 away, we get 46. Again, please do not graph it. Ay, that's a large number. So just write it as a coordinate to show that you know where it would be if you were to graph it. Sweet. All right, ladies and gentlemen, we have one more example. This one is muy importante, super important, because we have a b value. And if you need to, please write that you have to factor the b value out first. Always, every single time. So do that with me, please. We have negative 2 on the outside. Our b value in the equation is 1/3. So for those of us that need the visual, when we factor, we're dividing, right? So 1/3 divided by 1/3 leaves us with x. But if I have 1 divided by 1/3, really what I have is 1 times the reciprocal. So that leaves us with x plus 3. Plus 5 on the outside. So let's identify the transformations, shall we? For A is negative 2. And as you've heard me say in the past, I'll always write it as two separate numbers, a product of such, because that helps me to see the visual. Oh, I've got two different transformations. The first one is a vertical reflection because of that negative 1. Then we see that A is 2, which is greater than 1, so it's a vertical stretch. Our b in the equation is 1/3, which means that we will use the reciprocal, 3. That implies a horizontal stretch. The h, taking the opposite sign, is a negative 3. So we have 3 units left. And the k is 5, which means we go 5 units up. All right, now I can't see it on my screen, so in case you need it again, we have for our transformation table the reciprocal of b being multiplied to x, and then we have plus or minus h, depending on what our h value is in the first column. We then take a and multiply it to y, plus or minus k in the second column. And this doesn't change. It will always be this same transformation table. All right, well, following that idea, we would have 3x minus 3 for this function and negative 2y plus 5. And yet again, as I have said, I'm going to write the parent function points right next to it. So it's easy reference. I don't have to sit here and try to remember what they are. All right, taking the first x, I have negative 2. Substituting it into the column, negative 2 times 3 is negative 6. minus 3 gives us negative 9. Negative 1 times 3 is negative 3, minus 3 gives us negative 6. Fill out the chart with me at this point, please. And then for the y values, 4 times negative 2 is negative 8 plus 5 gives us negative 3. 1 times negative 2 gives us negative 2 plus 5, which is 3. And then we can finish from there. And let's graph it. Keep in mind, the vertex is always in line with 0, 0. It's always the HK. It is always able to be pulled from the equation if you're given it in vertex form. Okay, negative 3, 5, 0, 3. 1, 2, 3, 1, 2, 3. Yep, I am just reflecting. Why? Because I can. And make sure, please, that when you graph it, you try to make it as curved as possible with arrows at the end. Excellent. Here we go. HK, we just talked about that. It is negative 3, 5. Poop. Again, we see there are going to be x-intercepts, but we don't know what they are. Please do not assume they are at integers. Always algebraically find them. Fantastic. We do have our y-intercept from the transformation chart, so we can put in 0, 3. The domain is still all real numbers or negative infinity to positive because there aren't restrictions on the function as far as the x values are concerned. This parabola opens down, so we see it has a maximum value. That's different than the previous two. So we're going to say that y is less than or equal to the k value or negative infinity to 5 inclusive. Unlike the other two, this graph increases at the beginning. So we say as x goes from negative infinity to negative 3, our x values increase. And as x goes from negative 3 to infinity, the y values decrease. It is not one-to-one. The rate of change varies. Our axis of symmetry is still x equals h, so we're going to say x equals negative 3. As we talked about, the maximum value exists this time, so that's 5 without a minimum. And the asymptotes still do not exist for a quadratic function. Last but certainly not least, our x-intercepts. Here we go. All right, we're going to do what we did in the previous example. Substitute 0 in for y. Now, it doesn't matter if you use the factored form or the original given. I always like to use the original given, but that's just my personal preference. And we need to isolate the quantity. Here we go. Subtract 5 from both sides. So negative 5 is equal to negative 2 times the quantity of 1/3 x plus 1 squared. Divide both sides by negative 2. So we get 5 halves is equal to the quantity 1/3 x plus 1 squared. We then need to take the square root just like we did before of both sides. So we get 1/3 x plus 1 is equal to plus and minus. Again, if you need to, write that down. The square root of 5 halves. Why do we have the plus and minus? Because we took the square root while trying to solve for the unknown variable. All right. Uh-oh. Do you see what I say? I see a radical in the denominator. I see that because the square root of 5 halves can also be written as the square root of 5 over the square root of 2. Mathematically, this is inappropriate notation. So we rationalize the denominator by multiplying the square root of 2 over the square root of 2. We do this because it is a square root. In the numerator, we can multiply across. They have the same index. They are both square roots, so we get the square root of 10, and in the denominator, we just get 2. The radicals ultimately end up canceling each other out. So we get 1/3 x plus 1 is equal to plus and minus the square root of 10 all over 2. I'm going to subtract 1 to both sides, so we get negative 1 plus and minus the square root of 10 all over 2. And in order to get x by itself, we have to multiply by the reciprocal. So I'm going to multiply both sides by 3, and I get x is equal to -3. I'm distributing that 3 plus and minus 3 rad 10 over 2. Woo woo, good stuff. And of course we're not 10 because we have to write it as a coordinate. You again are more than welcome to write 2 separate coordinates, plus and then minus, or you can write it as one. Excellent job.